Okay.
That's too bad. I was brilliant.
Yeah, you were. Okay. This is actually a circuit construction kit. I did send out an email with a listing of all these things, where to download these. But circuit construction kit has all of these components. And here I have a battery. You can actually, by clicking on it, you can adjust the voltage, and you can see what kind of results you get. You can also, here you have an ammeter. It's showing current going. You see it broke the line, so the current has to go through the ammeter to show its value. And here's a voltmeter, and it shows the it's parallel to the voltage source. I'm showing here the electron flow, and there's also a separate resistor, which you change it, and you can see it varies the voltage. It varies it'll vary the voltage, and it'll vary the current thereabouts. Okay, and these are things that you can play with. Right now I have this thing set to 34 ohms. I can set it to 0 ohms, and that's how it actually works. Anyway, this is something you can play with, and actually demonstrates the Ohm's law that Bob is going to talk to you in a little bit about.
Okay. And I'm glad you pointed out that the voltmeter was connected in parallel and the ammeter was connected in series. Okay.
Mm-hmm.
Okay, back to work. And we've been through parallel. Oh, practice questions. Let's not do those. Let's not do those. Let's just move on. That was A. Yeah. Now is the time. Okay, Jerry, am I sharing?
Yes.
Okay. Now is the time we talk about Ohm's law. Ah, yes. This is a cool thing. And I know when Jerry does this chapter, sometimes we switch off chapters. He usually does this, but I'm doing it this time. But when Jerry does this chapter, he often suggests when you go to take your technician exam, you're going to get a piece, you're going to get the exam, and you'll have a writing utensil, and you'll have a blank piece of paper, for whatever. And he suggests, and it's a great idea, is the first thing you do when you sit down with that is you take that blank piece of paper and you draw this circle, split it in half, and on the top half you put the E for electromotive force or voltage, and on the bottom half you bisect that and you put in your I and R. All right, because there will be some questions, or there could be, almost certainly there's going to be at least one question that's going to ask you to calculate one of these elements knowing only the other two. But it's really, really easy.
You use your thumb.
You use your thumb. And I don't know. Okay. For instance, if you're given the amps, the current, the amps, and the resistance, the ohms, and they ask you, well, what's the voltage? Well, it's easy. You just, you cover up the E on top, and you look at I and R, you multiply them. I times R, amps times ohms. that will give you volts. Or if they give you volts and resistance, so they give you volts and ohms, well, you take the ohms, divide it into the volts. So if you have 10 volts and 2 ohms, and you want to know how many amps you have, you divide the 2 ohms into the 10 volts, and that tells you you're going to come out with 5 amps. It's that easy. It's that easy. But it's really best to just go ahead and draw that little circle and keep it there. It will keep you calm through that section of the test. Okay. And we will look at some of these. All right. What formula is used to calculate current in a circuit? Current? Well, current is amps. That's intensity, I. Okay, so what is that? You're gonna, okay, remember the E is on top. Okay, so you're gonna divide the E, you're gonna divide it by the resistance in ohms. Okay, so current equals voltage divided by resistance. Okay, what formula is used to calculate voltage in a circuit? Well, amps times ohms. All right, voltage equals current, or amps, amperes, multiplied by resistance, or ohms. Amps times ohms. And what formula is used to calculate resistance? Okay, voltage divided by the current. Voltage, volts divided by amps. This is easy stuff. Okay, here's a couple of little story problems. Okay, what is the resistance of a circuit in which 3 amps flow through 90 volts? Well, 90 divided by 3, 30. Simple stuff. All right. How about resistance in a circuit for which 12 volts, 12 volts applied, and the current flow is 1.5 amps? Well, volts and amps, divide the 1.5 into 12. That's going to give you, of course, 8 ohms. What's the resistance of a circuit that draws 4 amps out of 12 volts? 4 amps out of 12 volts. Okay, so you're going to take your volts, 12 divided by 4, 3 ohms. Man, it's that easy. You know, when you get to these questions, I want you to be not just comfortable, but happy that you got some easy questions to get through.
Now this can have some practical applications to you. For instance, if you have a radio that draws 20 amps and at 12 volts. Okay, so okay, so you have 20, you have the current, you have the voltage. So what's the resistance? And you're going to right? Bob, figure it out. E divided by 20, so it's 12 divided by 20 equals 6 ohms. Yeah, 0.6 ohms. And that kind of resistance, you're going to see that a wire is going to have to be a certain size to be able to carry that. I made a mistake like that once and managed to some spectacular fireworks because the wire was too small. Okay.
Okay. All right.
Yeah, for something like that, you're going to have to figure out how large a wire, and there are charts that'll show you the resistance of various wires, so you don't get the wires to heat up too much.
Okay. This is a particularly easy one because you're dividing 100 ohms into 200 volts for 2 amps. All right. What's the current flowing through a 24 ohm resistor? 24 ohm resistor connected across 240 volts. Okay. We're going to divide 24 into 240. That's 10 amperes. Okay. What's the voltage across a 2 ohm resistor if a current of a half an amp flows through it? What's the voltage? Well, all right, now this, you have ohms and amps. You multiply those, and that's going to give you 1 volt. Okay, the voltage across a 10 ohm resistor, if a current of 1 amp flows through it, that's even easier, 1 times 10. Okay, what's the voltage across a 10 ohm resistor if a current of 2 amps flows through it? 20 volts. Okay. Power is work over a given segment of time. Okay. And again, electrons moving through resistance expend electrical energy and consume power. Well, current flowing through a resistance expends electrical energy and consumes power. Power is the rate that it's consumed, and power is measured in watts. And power is the product of voltage and current. Voltage, E, and current, I. So amps times volts equals power, or watts, all right? But if you know the watts and you know the amps, you can find the volts. Just like if you know the watts and you know the volts, you can find the amps. If you know the amps and the volts, you can find the wattage. All right, it's just like the other one. And on that piece of paper, you might as well draw this second circle with the famous letters there, pi, P-I-E. Okay, just remember that the P is on top. All right, watts, the power is on top. Power is always on top. Okay, and then, you know, it's, oh yeah, it's just the same as the other one. No sweat. All right. And that we're not going to do right now. Let's stop sharing. And let's march right out. You know, before I go, any questions on that? That's, I think, pretty straightforward stuff. Okay. I think that's a section of questions that you should hope to get on your exam. You know, lots of them, because they're really pretty easy, you know. Okay. You see, oh, now this is the fun part. And I expect, Jerry, I expect you to hop in on this a lot.
Well, we'll see.
This is a part of the presentation I call parts is parts.
That's just parts. Oh, I have to dip into my magic box.
Okay. All right. To make anything work, you know, you need to manipulate the current and the voltage. All right. And you do that with the use of resistors and capacitors and inductors and relays and switches and all kinds of fun stuff, transistors. Okay, schematics. They talk to you about schematics. Those are very, very useful stuff, especially for any of you intrepid hobbyists who want to start playing around inside your radio. That's very, very good stuff. Okay, schematic diagrams. Okay, there was that section in your book that gave you all the cool little diagrams. Now, this one, what we have here, we've got this Okay, the lines and dots on the schematic, yeah, yeah, all this stuff represents components, okay? The resistor is just the squiggly lines, right? The zigzags. And you'll notice that, and I think the book pointed this out too, is that in these diagrams, they'll be designated with numbers. All right, so we have multiple resistors in this diagram, so they're numbered. And if this was a very big schematic, those numbers could go up, quite high. All right, in here, we have this wonderful little transistor. All right, in fact, this is that bipolar junction transistor. And along here, of course, again, what we have here is an ammeter. Now the ammeter, you'll notice again, this is in series, whereas, this resistor here, this is in parallel. Okay. The resistor. Resistors, all right, their whole purpose, it helps you control the circuit. It helps you by resisting or obstructing the flow of current. Resistors come in all different shapes and sizes. Let me show you a few. Here's a resistor, right? Now, later on, I think in your general, if you go on to the general license, they'll get you to learn what those stripes are for. Those stripes are numeric values, okay?
They're color-coded, and that's why none of my early electronic projects would work, because I found at a late age that I was red-green colorblind.
Yeah. Okay. There's another another resistor. This is also a resistor, but this is a variable resistor, and by twisting that little thing, you adjust the resistance. This is the thing they also called the potentiometer. Okay, but it's just a variable resistor.
Yeah. And there's usually an arrow that is attached to the inside of the squiggle. That arrow shows that it's variable.
Oh, yeah. And then there are also resistors for circuit boards, and and they can sometimes look like this. So, okay.
Now, some of the resistors, I don't know, do you have a power resistor there?
No, I don't really know. How about this?
Let's twirl it around. Yeah, okay.
That's a wire wound resistor.
It's a wire wound resistor, and it has this kind of heat dissipating material around it. Don't touch it while it's because it does get a lot of heat. There are some that are made out of that have a casing on it. I wouldn't be able to show it, but looks something like this, and it actually has fins to dissipate heat, and you can attach it. You can attach it to a chassis, so the chassis will absorb heat as well. That's for applications where this is going to dissipate a lot of heat.
You should call those power resistors.
Pardon?
I said we usually call those power resistors.
Power resistors, yes. And they're used for various things. Some are just to fine tune a circuit, get the right kind of voltage to a transistor, so they can be quite small. If you take a look at some of the little radios you've got, some of these quarter or eighth watt resistors are very tiny compared to a power resistor, but that's all it's needed.
Okay. Yes, and here are the symbols for this is a regular old resistor, this top one. The bottom one, like Jerry said, with the arrow, the arrow shows that that's a variable resistor, also called a potentiometer. Okay, capacitors. Capacitors are cool things. Capacitors actually store energy. They store energy in an electrical field. They come in all different kind of shapes and sizes. This is a capacitor.
Two conductors with an insulator in between.
This is also a capacitor.
A lot of these round ones, you have an electrolytic. Yeah.
That's a honker.
Yeah. And what makes it a honker is that it's a kind of sandwich. You take two long strips of tin foil or some sort of conducting material and get some wax paper sandwiched in between, and you roll it up. Sometimes they'll put a chemical in there to increase the capacitance, and you can get some really high values of capacitance.
And those are other capacitors. Okay.
And actually, there's smaller values of capacitance. I don't know if you can see this one. If you want to pin on this, this is my egg slicer. And what it is?
Yeah, now that's a variable capacitor.
It's a variable capacitor. It's, you can change it, and you have the conductors, which are these plates. But what is the insulator here? Anybody?
Air.
What's the insulator?
Air.
Exactly.
Okay.
Yeah, exactly. Air.
With the spacing here, you can put several thousand volts through the capacitor without it arcing out.
Okay. Okay. And yeah, this is the symbol for a capacitor. It shows you like the two electrodes with a space in between, and that space can be some kind of a material, some kind of an insulating material, or it could be air. And again, that same symbol with an arrow through it, that's a variable capacitor.
And there, I remember seeing a photograph of one of Marconi's capacitors for one of his high power radio stations. And the thing was a room, probably, I don't know, 20 foot by 20 foot, with a lot of glass plates and air between. That was a capacitor.
Okay. And then an inductor. An inductor also stores electrical energy, but it stores it in a magnetic field. Its schematic is this bumpy little thing, almost looks like knuckles. And again, with the arrow through it, that's a variable inductor. Usually inductors look something like, they're coils basically. They can be different, but either coils wound around just with air in between, or they can be, with this other one on the right at the bottom that has it's wound around a toroid. A core.
It's a donut shaped piece of material that will increase the magnetic field.
Mm-hmm.
That's a fairly recent thing. The use of toroids used to have very large coils, and now with a toroid core, you can decrease the number of turns on the coil and still get the same magnetic field.
Okay. Then transformers, very, very useful stuff. Okay. Transformers, essentially they're made with, you'll notice a very familiar symbol. Yeah, inductors, usually two inductors. Now, the number of turns on each side of the core, all right, there's a core in between. The core can sometimes be air, or it can be some metallic substance. Now, the number of turns on each of the coils depends on what the transformer does to the current that's coming into it. Now, it can either increase voltage or decrease voltage, again, depending upon the ratio of the turns on the one inductor to the other.
Okay, it should be noticed that this only works with a changing magnetic field. It could be an alternating current, or now back in the 50s, there was a gizmo called a vibrator that would turn the direct current on and off very rapidly. When it turned the current on, it would create a magnetic field. When it turned it off, the magnetic field would dissipate and induce electrons to flow in the coil. So two ways of doing it: either switching on and off or using alternating currents. And of course, the same principle works with the radio frequencies that we have, very, very rapidly changing currents.
Okay. Okay. Oh, yeah. All right. Now, resistors, we've talked about resistors before, and you measure resistance in ohms. Capacitors, they have capacitance, but that's measured in units called farads.
Faraday.
And Michael Faraday, another Britisher. And then inductors, the unit of inductance is the Henry, after
Henry.
Well, I didn't think it was Malcolm, but I don't know the guy's first name. Okay. And we talked this thing, and we talked about that. When there's multiple repetitions of a particular component in the schematic drawing, they'll be numbered. Okay. Resistors, they're always in the schematics with an R. Capacitors with a C. Inductors with an L, for a reason which I forget at the moment. Okay, indicators and displays. Oh yeah, indicators. Yeah. Indicators just tell you the status of the equipment, what's going on. Whether it's on or off, that's the blinking lights or whatever. LEDs, again, are used to show, if something's on or off. Displays are different than indicators in that they usually give you a number or text or something of that nature. Okay, reactants. Now, way in the beginning, when we started talking about resistance, I told you there was more than one type of resistance, all right? Capacitors, we talked about them. Reactance is resistance in general. Resistance, when we talk about resistance, we're usually talking about opposing current, okay? Resistance can either oppose direct current or alternating current. But when we start talking about reactance, we're talking really about opposing alternating current. Okay, so that's what capacitors and inductors are used to do, to kind of moderate alternating current. Okay, yeah, energy storage, it creates reactants. Oh, reactants, yeah, that's a symbol X. We get a lot of symbols in this chapter, and that's okay. Okay, capacitive reactants, the reactants from a capacitor, it's designated with an X, small c. Inductors have inductive reactants, that's an X with a small l. And the effects of these can be complementary. All right. Impedance is really the generic term for resistance. All right. So the combination, yeah, the generic term is impedance, and impedance includes both resistance and reactance. All right, so resistance you're going to get specifically from resistors and other types of components. Reactants you'll get from capacitors or inductors. The sum of all that resistance you get from all that, yeah, is called impedance. All right.
Okay, can I?
Yeah,
Can I?
so impedance does include both opposition to alternating current and direct current, whereas reactance is only opposition to alternating current. Okay, Jerry, take it away.
Okay.
Let me stop sharing.
Okay. Well, you're gonna have to pin on me. Set your little monitor to pin on my camera. All right, I'm showing you a set of coils. I use this in my antenna tuner. It's very ancient, and you can see that there are it's fairly heavy wire, all coiled up like this. And if you put an ohm meter on this, you're going to find it's very, very few ohms. A lot of current is going to flow through this thing if it's direct current. And you can see this one in the middle is not attached to anything. That goes to the transmitter, and it creates a magnetic field which excites these secondary coils. The thing is, when you get away from direct current, when you get into alternating current, when the alternating current is turning on and off at a very, very rapid rate, like 30 megahertz, that's 30 million times per second, this is going to show an awful lot of resistance. So that's, or call it impedance. And that's why you see antennas and things like this. And where's the impedance? Where's the resistance? It's there, but you have to get up to very high megahertz. This thing would probably, well, I use it for tuning in the 25 megahertz to 50 megahertz band. Something else. Yeah, this is a little better. You see, it's more coils of wire. It shows more impedance in a lower frequency, probably around 7 to 14 megahertz, thereabouts. But this is the kind of impedance that we talk about. This is the kind of transfer of electrical power. Okay, Bob.
Okay. Okay. All right. Resonance. Resonance is where you want to be. Okay. Now, think of capacitive reactants and inductive reactants as kind of being kind of like opposite sides of the coin. When you can get your circuit to where your capacitive reactants and your inductive reactants are equal, they cancel each other out. And so the resistance that they provide within the circuit kind of goes away, and the only resistance left in the circuit is that produced by your resistors and by the wires. So you're left, so your total impedance is not reactance plus resonant or resistance. It simply ends up being the resistance. That's what you do when you're tuning in a radio, is you're adjusting your inductors and your capacitors to hit this point where they are equal and they cancel each other out, and you are resonant, and you get your station in as clear as it can be. Okay, and that's referred to as the resonant frequency when the capacitive reactants and the inductive reactants are equal. That's kind of a tough concept, but
Well, if I can get this cable free, I might be able to show something about that.
okay, I'll stop sharing.
Pinning on me again. This is my 70 or 80-year-old antenna tuner. Takes the antenna. This leads up to my antenna outside. It goes into this box, and you can see that there are the coils I showed you, and some capacitors. These are ganged up in a way to transfer the power. I will use this particular capacitor to tune the antenna to resonate with the transmitter. And when you now, the resonance can be used in two ways. It can be used to either pass the radio currents, the RF energy through, or it can keep the resonance, keep the power from going through. I don't know. I guess we can show that a little later with beam antennas when we get to that part, because I have what's called a tri-band beam. It's an antenna that's electronically shortens itself or lengthens itself depending on the frequency it's on. We use these resonance circuits as traps to allow power to go through or to reject it. Okay, Bob, back to you.
Okay. Am I back to sharing?
Yes.
Okay. All right. Oh, resonance or tuned circuit. Resonant, yes. Okay. You see this top section up here, this top part of the drawing. And this shows, you got this nice inductor, and you have this capacitor in parallel. And when the two of those, when you adjust them so the two of them, the reactants of the two of them are equal, they cancel each other out, and you hit this resonance. You create a resonant circuit, also called a tuned circuit. Okay, semiconductor components. This is cool stuff. Semiconductors, they're made of layers of material, of semiconductors. Semiconductors, they conduct somewhat, but not very well.
Maybe it would be best to explain it with insulators and conductors. I don't know if we've gone through that yet.
Let's see if we got wait a minute. Well, I should, I don't know if we have a picture of that.
Oh.
We don't, okay. Well, the deal is, let me get back to where I was. Semiconductors. Semiconductors are a layer of materials that is usually like a two semiconductors, usually with a third layer that may be an insulator, and one of the layers will be heavily positive, the other will be heavily negative. And what you want to do is, by varying voltage and whatnot, you get it to do what you want it to do. Okay? Now we're talking about more parts, okay? And this is the diode. The diodes is something with a couple of electrodes. The schematic looks like, a line with an arrow and a and a breakpoint in it. Physically, they're not always very exciting things. Here, let me show you a couple. Now, somehow I still have you pinned.
You should be able to find on those three dots, you should find an unpin.
Huh.
No? Yeah,
No, I'm still just seeing you when I don't share. Oh, I'm not complaining, mind you, but
okay, but I think you can find more attractive things to put on the wall.
Okay. All right. Anyhow, all right. So here's a diode. That's a nice diode. Here's another diode. This is just a bitty one. Okay. What diodes do, diodes are important. What diodes do is they allow current to flow in one direction. And let me go back to, okay. They allow current to only flow in one direction. Now that's very, very handy. Turning something into direct current, turning alternating current into direct current. There's actually a specific name for that. If you're using it if you're using the diode for that purpose, that's actually called rectification. And that particular kind of diode is referred to as a rectifier. But there's other stuff you can do with diodes. And one of those, the kind of a fun one, is this thing here. You see this? There's these different symbols are different specific kinds of diodes. One is a Schottky diode, the other is a Zener diode. But this one here, check this one out with the little arrows going off it. That's a light emitting diode. And that's a thing that lights up on equipment that lights up, numbers or text. Those are diodes. Very, very useful things. Okay, transistors. Oh, yes, the transistor age. I'm old enough, I remember just when when I got my first transistor radio in 1961, I think it was. They were, oh my God, they were all the rage, and they were thought to be just Oh, just the berries. Transistors are really useful. They can be used to amplify, or they can be used to with a very, oh no, what did I do there? They can be used to control current or energy. They by using a small amount of energy, they can create, control large amounts. Transistors, they here. Let me show you a couple. This is one type of transistor. Here's another one that would go on a circuit board. Hey, there's one. So, and then here's a real little one. They come in all shapes and sizes. You see, this one's got 3 little prongs on the bottom.
These are very, very old-fashioned types of things. If you look in your computer and you see the processor in there, there are probably several billion very, very tiny transistors inside that.
Yeah.
You have these little switches, or if you put a little current on the base of a bipolar, it'll control a large flow of current. It's almost like a little faucet on a water line. Doesn't take very much effort to adjust the faucet, but you can get control a lot of water flowing through it.
Mm-hmm. Yeah, your book talked about 2 types. One is the bipolar junction transistor, 3 layers of NRP material. There's 2 types: the NPN, which has 2 layers of highly negative material, and the other called the PNP, which is more of the positive biased transistor. This one here that you see, this is an NPN, and you can tell that because the arrow is pointing out. So the way you remember this is that it's an NPN because the arrow is not pointing in, okay? Whereas if the arrow was pointing in, it would be pointing in proudly. Okay, but this is an NPN. There are 3 parts to this. There's a base, a collector, and an emitter. Then the field effect transistor.
The current flows from the emitter to the collector. That's why it's a little confusing because the arrow's pointing that way.
Yeah, right. Mm-hmm.
But depending on the voltage that's on the base, it'll control the amount of current that's flowing from the emitter to the collector.
Yeah.
The same principle on the next one, the junction transistor.
Yeah, where you apply the voltage to the base, and then the current comes into the emitter. This one, they call it different titles, but it's the same kind of thing. You've got the gate, which is where the voltage comes in, and then the source and the drain. The drain, that's probably where you're doing your work, where you have the work connected. Okay. Yeah, and it's the gate. What they're saying here, yeah, the gate controls the current going through this channel in the transistor. Okay, and then the integrated circuit. All right. Yeah, there could be all kinds of stuff on this thing here. And these are 2 different schematic symbols for them.
Right, there's a whole bunch of parts in it. That's why it's called an integrated circuit.
Yeah, parts is parts.
And again, this is something that's, a mile wide and half an inch deep. You
Yeah.
don't have to know too much about those until you go to the general and extra class exams.
Yeah, but for the technician class, you don't need to know a lot about it. Just a very little. We're trying to get you through that part. Okay. Okay. Protective. Here's more components, more parts as parts. Okay. These fuses and circuit breakers. Fuses. Yeah, they just protect you from surges in current, and the little hair-like whisker in there. If you get a bad surge, it'll just blow. It's meant to. Um, uh, Other than that, and the schematic for the fuse is this second drawing right here. All right, with the little whiskery thing in it, which blows. And then there's a circuit breaker. It does the same thing. Cool thing, of course, circuit breakers can be reset. When you blow a fuse, you have to replace it. But whereas a circuit breaker, you push the button, reset it, and you're good to go. Okay, switches. Now they go through a lot of this thing about the poles and the throws. Okay, each position that you can do is called a throw, and so this. Oh, in the circuits controlled through the switches is the pole. Okay, so you have single pole, single throw, where it's either open or it's closed. Okay, you only have one thing to do with it. You can have a single pole with a double throw, where you've got one source, and it's going to be one of two positions. Okay, one of two positions, and then the double pole, double throw, where you're
like this one.
yeah.
This is
There you go.
Yeah, Dr. Frankenstein's switch.
Yes. You don't see a lot of those anymore, but the push button you see lots of these days. Okay. And the push button, not only the push button, but just the LED that you just put your finger on. So
I was using this for my antenna because I was using that ladder line, which has two conductors, and I needed a lot of distance between the contacts, just in case there's a high voltage.
Okay. And the other thing are relays. Relays really, they're switches, but whereas with a switch, you have to do it. You have to throw the switch. Relays, they're activated within the circuit. Okay, so that's
electromagnets actually pulls the switch for you.
Yeah. So
you have to push a switch button or something of that sort to make it active to make the real switch.
Yeah, and then when the right condition occurs, then the relay works. Okay. Relays can be in positions normally open or normally closed. Okay, and then all the fun symbols. You saw them, you love them. Okay. And I think that's about it. Oh, I'll bet you've got lots and lots and lots of questions. Because if you don't, I do.
Yeah. All right. How many people are dazed? We did a lot of material, and this is probably one of the tougher things to absorb. You have to take it piecemeal, a little at a time. Again, it's a mile wide and an inch deep.
Yeah. And again, it depends on how much exposure you've had to this field before. If you've worked in electronics or been taking a lot of physics or something, this may be all old hat for you. But if not, but again, this material it's relatively interesting, and not really that difficult. Just kind of wade your way through it. let me see here. Now, I was not kidding that I had questions. Jerry, I'm sharing now, right?
Yes, you are.
Okay.
Right.
All right, look, again, you know, my purpose here is to get you through this exam. So look, we've kind of covered the whole chapter. Now what I want to do is I want to quickly run you through all the questions that might show up on your test arising from the subject matter that's been in this chapter. Most of these things are going to be so easy for you, but I want you to see each of the individual questions, and we're going to go through them. It's not going to take us too long, but we're going to go through them. Just so when you hit these questions, man, you are going to be so happy because you'll know them cold. Okay? All right. Electrical current is measured in which of the following units? Okay, current. Current is designated by the letter I, and it's measured in amperes. Okay, amps. What's the name of the flow of electrons in an electric circuit? Current, right? And it's really the current that flows. It's really the charge that flows, but okay, we're saying electrons flow. We'll just wink and bypass that. Okay, what's the name for current that flows in only one direction? This would be current like that comes out of a battery, and that's direct current. And what's the term for electromotive force that causes electron flow? Remember, that's like the force that causes the pressure that pushes the current. Yes, that's voltage. What's the term for the current that reverses direction on a regular basis? Okay, that's alternating current. That's the opposite of direct current. What's the unit of electromotive force? All right, remember, electromotive force is the same as voltage, and it's the volt. Okay. Oh, and it's sometimes called electrical potential. Okay, electromotive force, electrical potential, voltage. It's all the same thing. Okay.
You're going to notice a lot of duplication in some of the questions. And that's done on purpose because we have, let's see, I think the ARRL is increasing the number of versions of the exam. I think we probably have about eight versions of the exam. Just so if you're sitting next to someone else who's taking the same test, the exam questions are going to be scrambled around. So you're going to have to be aware of the different wordings and stuff, so you'll be able to answer the questions.
Yeah, and another point, you know, if you're gonna if you find there are sections that are difficult and you want to get through it just by memorizing the answers, which people can do that, but remember that take this first question here. Electrical current is measured by which of the on page 1. I should be on page 2. Okay. Which instrument would you use to measure electrical potential or electromotive force? Well, of course, that's voltage. Now, on a question like this, this is the actual question you'll see. These are the actual answers, but they might not be in this order, okay? So, like when you look at this question, what instrument would you use to measure electrical potential? Don't memorize B as the answer. Memorize voltmeter, because voltmeter may be, you know, on your version of the exam, voltmeter might be choice C or D or A, you know, so. Okay,
Hey,
so
Bob,
learn the
question,
terms.
Bob, so with the questions, they must have a pool, and every time they give out a test, they change those questions and they can change the order of them, right?
Well, the question pool is the same. I think 420 some questions or something. It's the same number. It's the same questions. It's just that each exam only has 35 questions, and they're not the same 35. And sometimes the choices are shuffled around. Okay, but But these are the actual questions, okay?
Okay, and they're all in the back of your book. In the back
Yes,
of your
they are. Yeah, they are. I just did it this way so you could see, what's coming out of each section of the book. If there's some of these, if we get into a section like this next section, circuits, if you're having problem with this, go and review section 6.1. Okay. Okay, which instrument would you use to measure electrical current? Current is an ammeter. Okay. In which type of circuit is current the same through all components? Remember, the same current through all components. That's a series, right? In a series, the current only has one path to go, so the current is the same in all. And in which type of circuit is the voltage the same across all components? Okay. A parallel circuit, the voltage will be the same. The current won't necessarily be the same, but the voltage will be the same. Okay, what happens to the current at the junction of two components in a series? Well, two components in a series, they're going to get the same current. Okay, so what happens to the current? The current's unchanged, all right? Remember that one schematic that had like the 3 light bulbs all in a row? They're all getting the same current, okay? Now, what happens to current at the junction of two components in parallel? Okay, two components in parallel. Now the current is not the same in a parallel circuit. It divides. Now, those components, if they have different resistances, they're going to get different amounts of current, right? And why are they going to get different amounts of current? Because they have different resistances, but the voltage is the same. All right, so if one of those elements is different, the third one will be. Okay. What's the voltage across two components in series with a voltage source? Okay, the voltage across two components in series. Okay, two components in series. Okay, now remember, in series, the current doesn't change, but the voltage does. Okay, so it's determined by the type and value of the components. Okay, and what's the voltage across two components in a parallel circuit? Well, remember, in a parallel circuit, the voltage does not change. The current can, but the voltage does not change. So that's the same. All right. What is the correct? Okay, here we go. What is the correct way to connect a voltmeter in a circuit? Now, remember back to those two diagrams, how you connect a voltmeter? You connect that in parallel. Okay, you can't just put it in the circuit, okay? Now, how is a simple ammeter connected in a circuit? And again, remember back to that one schematic, it's connected in series. Okay. Ohm's law, which of the following is a good electrical conductor? Well, of course, metals are the best conductors, so, and the only metal there is copper. All right. Now, which of the following is a good electrical insulator? Well, if metals are good conductors, then you want to pick one of these that's not a metal, and that would be glass. And what instrument is used to measure resistance? An ohm meter. That's pretty that's pretty logical. Okay. Now some of these, we actually did these questions when we were going through the PowerPoint slides. So well, we'll do them real quick. All right. The formula used to calculate current, okay, voltage divided by resistance, volts divided by amps, or ohms, volts divided by ohms. Okay, the formula to calculate voltage, amps times ohms. Okay, and the formula used to calculate resistance, voltage divided by amps. Okay. Now, and I think these are the same questions that we had. So 3 amps through pushed by 90 volts. Okay, that must be 30 ohms. All right, 12 volts with a current of 1.5 amps. That must have a resistance of 8 ohms, right? 1.5 divided into 12, 8 ohms. And I think, how are we doing on time?
Oh,
We're
we
not
have
doing,
almost a half hour left.
okay. All right. Oh, okay. I'm going to skip through some. We did all these before. Did anyone have any questions on these? No, we're good. All right. Okay, now let's review. And we talked about power. Now, electrical power is measured in what unit? Electrical power is watts. It's kind of funny. You may wonder why I'm going through this with the answers already highlighted. The first time I did classes with Jerry, that was about 3 years ago. Actually, it was 3 years ago this month. So, time flies when you're having fun. Any rate, and I was doing this on chapter 6, which is one of the administrative chapters. But I actually had copies of all these, and what I did is I handed them out to people in the class. We actually had a big class that time. We had like about 14 or something. The thing was, it was a good learning experience. It just took too much time. I mean, it just took too much time. So I've tried it a couple of different ways, and it's, what I really want to do is I just want to review the questions with you. Yes, I want you to see the answers. Yes, I want these answers to pop out at you. Okay? That's why we're doing this. And I want you, I know we tell you to go through the practice exams. I know not all of you will, but, and for those of you who are, well, you know what? This is going to make everything easier for you anyway. Okay, electrical power is measured in which units? Watts. What term describes the rate at which electrical energy is used? All right, power. Remember, power is related to time. Okay, so that's rate. Rated, okay? And again, the formula to calculate electrical power in a DC circuit, power equals voltage times current. Remember that chart with the pi? P, power, was on top, and then voltage, or E and I, voltage and amps, were on the bottom. Okay? So you want to find power, so you multiply those two. All right. How much power is being used when 13.8 volts is applied to a DC circuit with 10 amps? Okay, volts times amps is 138 watts. How much power is being used in a circuit when the applied voltage is 12 volts and the current is 2.5 amps? Well, 12 times 2.5 is 30. Okay, 30 watts. How many amps are flowing in a circuit when the applied voltage is 12 and the load is 120 watts? Well, okay. The watts, that's the P on top. You divide the 12 volts into the 120, you get 10 amperes. Okay, components, parts is parts. What's the ability to store energy in an electric field? Okay, now remember, you can store energy in an electric field, you can store energy in a magnetic field. When you store it in an electric field, it's called capacitance, and you measure that in farads. Okay, so capacitance, electric field, capacitance, farads. Electric field, capacitance, farads. Okay, and what's the ability to store energy in a magnetic field? Well, that's inductance. It's measured in henries. Okay, magnetic field, inductance, henries. And what electrical component opposes the flow of current in a DC circuit, in a direct, in a DC circuit, and that is a resistor. Okay. And what type of component is often used? As an adjustable volume control. All right. And that, of course, a potentiometer, a variable resistor. All right. You change the resistance, you change, the power. Okay. What electrical parameter is controlled by a potentiometer? Well, a potentiometer, remember, is just a variable resistor. So, of course, what parameter? It controls resistance. It's a variable resistor. What electrical component stores energy in an electric field? A capacitor. We kind of had that up here. Okay. What type of electrical component consists of two or more conductive surfaces separated by an insulator? Two or more conductive surfaces, that's a capacitor. All right. And what type of electrical component stores energy in a magnetic field? We've talked about that. That's the inductor. And what electrical component is usually constructed as a coil of wire? Remember, it's the inductor. The inductor usually looks like a coil. So it could be a big coil or a little coil.
It could even be a little hairpin.
Okay.
Or just a little squiggle on a printed circuit board, depending on how high frequency you are.
What component is commonly used to change 120 volt AC house current into a lower AC voltage for other uses? Oh, yes, a transformer. Okay, what is impedance? Impedance is opposition to alternating current flow in a circuit. Okay, impedance, opposition to alternating current. Okay, what's a unit of impedance? Impedance measured in ohms. Is any of these giving anyone any problems? We okay? All right. Which of the following is a resonant or tuned circuit? Okay. Remember, a resonant or tuned circuit has an inductor and a capacitor. All right. And they could be connected in series or parallel. If you remember back the diagram that I showed you, they were connected in parallel, but that doesn't have to be. Okay. So they're an inductor and a capacitor, and they form a type of filter. Okay, what class of components uses voltage or current signal to control flow, current flow? And that's a transistor. That's what transistors do. They use voltage to control current flow. Voltage or current signal, but still. What electronic component allows current to flow only in one direction? That's the diode, the very cool, very useful component. Which of these components can be used as an electronic switch or amplifier? A transistor. Yes, a transistor can be used to amplify. Which of the following components consists of 3 layers of semiconductor material? And again, that's the transistor. Okay. Which of the following electrical components this is kind of like the same question. Which of the following electronic components can amplify signals? That's the transistor. How is the cathode lead of a semiconductor diode often marked on the package? It's marked with a stripe. I don't think we talked about that. It showed it, and I think it showed it in the book. In the diagram of the book, it showed that the cathode of the semiconductor diode is, marked with a stripe. That's different than resistors that are marked with colored stripes, multiple colored stripes to designate the resistance values. Okay, what does the abbreviation LED stand for? Why? This is a gimme question. Okay, light emitting diode. FET stands for field effect transistor. Field effect. And what are the names of the 2 electrodes in the diode? The anode and the cathode, which are the same 2 electrodes in a battery. which of the following could be the primary gain producing component? Again, we've had 3 different questions to talk about the gain producing or amplification power of a transistor, and this is another one. I guess they want you to know that. Okay, what's the term that describes a device's ability to amplify a signal? And that is gain. Gain. You'll learn more and more about that as we go on. Which of the following devices or circuits changes an alternating current into a varying direct current signal? Okay, and that is a rectifier. Remember, the rectifier is a type of diode that specifically changes alternating current into direct current. Which of the following is commonly used as a visual indicator? Well, I hope you know this one is an LED, a light emitting diode. And what's the name of the device that combines several semiconductors and other components into one package? Well, that's the integrated circuit, which by now, our lives run on. What's the function? Let's skip that one because I don't have the diagram out in front of you. What component is used to protect other circuit components? Well, of course, that's a fuse. The fuse, or if, yeah, and this that's the only alternative they give you that's correct. They could have given you circuit breaker, and that would have been correct too, but they didn't. So, fuse is it. And what's the purpose of a fuse in an electrical circuit? And that's to cut off the power in case of an overload. And why is it unwise to install a 20 amp fuse in place of a 5 amp fuse? Oh, it'll let a lot of current through, but if that circuit is not meant to take 20 amps, yeah, that can cause a fire. That can be very bad. Yeah, circuits or fuses and circuits are rated for a reason. The wires and the components in the circuit, are meant to take a certain level of power, and, overjuicing them is not good. Okay, what electrical component is used to connect or disconnect electrical circuits? Well, that's a switch. And what's a relay? An electronically controlled switch. And what is the name of electrical wiring diagram that uses standard component symbols? That's a schematic. And what do the symbols in electrical schematic represent? Just electrical components. And which of the following is actually represented in electrical schematics? Okay, the way the components are connected. That's the thing about schematics. They're not necessarily to scale, and they're not actually maps. They're showing you the way things are connected. The physical positioning of the components could be a little different, could be a lot different. Okay, and what's the name of a circuit that generates a signal at a specific frequency? And that's an oscillator. And I don't think we talked about that. No, but that's okay.
Yeah, we can pick it up a little later.
Okay. Now, which of the following describes combining speech with an RF signal? And that's modulation. You have an RF signal, and to add information to it, whether it's speech or music or whatever, you're modulating the signal. Okay. And which of the following is used to convert a radio signal from one frequency to another? And that's a mixer. And that's I think the book, we didn't talk about it tonight, but the book talked about it, and it mentioned a little bit about a term called heterodyning. And that's where, you take 2 radio signals and you mix them, and the mixed products give you a different frequency. Okay, those are all the questions that could have come out of Chapter 3 that you might see on the exam. And how are we doing on time? We're at
We have about 12 minutes left.
12 minutes to 9, and Hugh, I have covered what I wanted to cover tonight.
Okay,
Good
Oh,
job.
and Jerry.
okay. Yeah, Bob, I wonder if I could possibly throw in something about the schematic diagrams. Just go over that a little bit.
Oh, yeah, go ahead.
Okay. Why don't you let me share the screen then? And
Screen sharing is on. Yeah, go ahead.
okay, I'm showing the 3 diagrams that are used on the exam, and it's pretty much just parts identification for the questions. But just to get into something here, you have a okay. You see these little forks down at the bottom here. What are those supposed to be?
Grounds.
Okay, they're grounds. They're assuming that the power supply or battery is grounded. And okay, this is a battery. The negative is grounded here, and the positive is hot. Now you're seeing a circuit. No, the grounds are supposed to be connected to each other. You're seeing a circuit here where you have a battery that is powering a light, and it would be working, except it's a transistor, and unless the base is charged at a certain voltage, it's not going to allow the current to flow. So that's what this transistor is doing. And you can connect almost anything here. Another battery for small voltage. You could probably even connect a microphone to this if it provides enough voltage. So when you talk into the microphone, it'll make the lamp flicker as it goes. All right, next one. This is a power supply, and it's a pretty well constructed one for a half-wave power supply. But okay, we know that this thing is a, what is that? Anybody? Well, that's a plug. See, one, it's a plug. The small terminal is the hot one, and it plugs into the wall. This is an F1, and now sometimes you have to buy them by the bushel. And what was something like this? What does an F1 do?
It's a fuse.
It's a fuse, which means that whatever's inside will melt if too much current is going through. There's a triple pole switch. Okay, everyone agreed? Triple pole double throw switch?
No.
Single pole, single pole. Single
Yes.
pole,
Single pole,
throw.
single throw.
Okay, good. Yeah, trying to make sure you're alert. Okay, we have these little bumpkins, which are sharing a magnetic field. So what we have here is probably something that's going to be stepped down from 120 volts down to maybe 12 volts, thereabouts. The D1 changes this alternating current into it's a pulsating current. It's only going to, if this is the line, the positive line, it's only going to show the positive parts. It's going to be positive voltage or flow current then nothing because it's blocking the negative of the sine wave, then another positive and another positive and another positive. So it's sort of hip hopping around.
Rumble.
That's not going to do. That's not going to do. So what do? We put a large capacitor here. And when the voltage is hopping up positive, what is this going to do? It's going to store electricity. And when there's no voltage, it's going to supply that electricity. So instead of hip hopping like this, it's going to wave a little bit, but it's going to be pretty much a direct current. If you get a large enough capacitor, it's going to make it pretty smooth direct current. All right, this device is really unique because it changes electricity directly into light, into photons. That's why they have the little arrows, light emitting diode. This is here to drop the voltage to something the light emitting diode can use. And then here, this is it's a squiggle. It's got with an arrow in it that shows that it's a variable squiggle. Anyone know what that squiggle is?
Potentiometer,
Oh, what?
the potentiometer.
You got it, potentiometer. And here, this is something unique that we haven't really discussed. This is also a diode, but it's a special one. It's called a Zener Diode. You can see the little squiggle here. And if the voltage is right, if it's going okay, everything's fine. It's going to sit there as if it's doing nothing. If the voltage goes up, this turns into a resistor that's going to pull the voltage down. And this comes to in different values. It's called a Zener diode. Okay. Next one, antenna tuner. This goes to the transmitter. This is well, it says ant. Doesn't look very buggy, does it? But that's our antenna diagram. And we have two egg slicers here, which are normally called what? Well, with the arrows there, it shows that they're variable egg slicers. Nobody knows.
Variable capacitor.
Capacitor.
Okay, variable capacitor. All right. Another little bunch of bumps. And that is called?
A variable inductor.
An inductor, right. And actually, this is pretty much a standard type of antenna tuner that's used today. And what it does, it's well, antenna tuner. It doesn't really tune the antenna. It just makes the transmitter happy so it doesn't blow up. We'll talk about how the transmitter can blow itself up if it doesn't see the right impedance. All right, I think I've taken enough time. I don't know, is anyone, I'm going to stop sharing, and I'd like to get some kind of an indication of Bob and Hugh and I were at the here Sunday for office hours, and we cracked a lot of jokes and stuff like that, but there was no one to crack them to except us.
I slept through your office hours. I'm sorry, I meant to come, but I didn't wake up. I want to come this weekend though, if you do it.
Okay, that's what I wanted to know, if we had it again, if people were interested.
I very much am. The schematics, I'm totally lost on. I have no background in electronics and it's very confusing. I was trying to look up the squiggles as you were pointing them out, but I'm just lost.
Sure. Okay. And all right, so I guess, Bob, should we try it again then?
Sure.
Okay, so Sunday, 1 o'clock, we'll be here. And
Okay,
Set my alarm
I'll
clock.
send out an invitation to everyone.
And, you know, we can talk about other stuff like, you know, things like this. This is the a bow thing. Or my trusty little Yaesu.
Mhm.
Various other transceivers. I mean, these guys look really good hanging from your belt, but how effective are they? We can talk about stuff like that too, if you want.
That would be very helpful. I actually got one of the Baofangs and it's so confusing. I'm too afraid to even turn it on. I don't even know if I know how to turn it on. I tried to read the guide and I don't understand it.
Well, no, reading instructions in foreign languages takes a great deal of peace of mind. But luckily for us, there are other people who've been there, have done some of the work for us, and YouTube has a bunch of tutorials, and I managed to find a step-by-step guide. You want this frequency, you want this tone, you want this bit, so punch this 3 times, this one twice, and all that. I've got something I can send you that will tell you how to program this thing. Of course,
Awesome,
you can only listen until you get your license.
Yes.
Okay, that's all I got.
Okay. Well, we're just about at 8:59, almost 9 o'clock. So we're right on time. Hey, everyone, thank you for showing up. It was good to see you. I hope we enlightened your your day. And
I have a real quick question.
Yeah.
Okay.
What is the date for the test, the exam? Is there a date scheduled for that?
Depends on where you are. There are exams, online exams all over the country. You make appointments for them. Here in our area, if the recreation department hasn't closed on February 1st, we're going to have an exam in Oak Park, Michigan.
Okay.
And if not, then we'll have to. Well, later on, I was going to get my daughter or someone else to describe how to take the exam and all that sort of stuff. But no, there's no deadline. You take it when you want, when you feel you're ready. When you're getting 85% passes on your online exams.
Rich, you're in Shelby Township, aren't you?
Right.
Yeah. Jerry, what club is it? I think it's the GM Club, or is it Usika? Q, do you know? They used to do exams like on the second Sunday of the month out at the proving grounds or something.
Proving grounds out there. Yeah, Yashika does that. As far as I know, they're still doing it.
Okay, Livonia is doing it, but they said they're full up. I just got a call from someone who wanted to take it. So we'll answer all those questions on Sunday.
Okay.
Okay.
And more.
I also have a quick question, Bob. I missed last week because of internet issues. And where do I go to find the recording?
We did record. Except Jerry, I'll have to send you the file. So
Actually, you have privileges on there. Well, let's get together and
okay,
we can put it on. There's Jerry's W9NPI YouTube
channel, yeah.
YouTube channel.
Okay.
And actually, I have to get rid of about 2 years of older recordings, but we can put it on there.
I'll check with you on Sunday then.
Okay, great.
Excellent. Okay, Well, that's it for tonight, everyone. Thank you much.
Thank you.
Okay.
Good night, Bob. Good night, Jerry. Good
Good
night,
night.
everybody.
Everybody.
Good
Have a
night.
good night.